Here we are out in the field for the very first ITM standalone CDAC 9139 field test. As you can see here, we constructed a customized rig to house all the hardware and various sensors. The brains behind the system here is the National Instruments CDAC 9139 chassis running Windows 7 embedded. Along with the chassis we have several input cards. We have 3 NI9233 modules collecting 10 channels of accelerometer data. We have a 9236 module where we are collecting 6 channels of quarter bridge strain data. We also included a 9239 module where we are collecting voltage data from our light tach sensor for rear axle speed measurements. The system has also been integrated with a wireless router as well as a wireless air card. This allows us to remotely connect to the unit during testing to configure our setups, initiate tests, view, validate, and retrieve data.
In our test monitoring area, we've set up a wireless hotspot that provides us with internet access. This also allows us the flexibility to connect to the chassis from any location using remote desktop or another remote access program. ITM's iTestSystem software has also been installed on the standalone CDAC. This allows us to configure a test by launching the software, and using the built-in configuration tools, we can see all the hardware that is currently connected. From here we can then configure and apply our channels and set up our tests remotely. We can then begin testing our sensor setup.
So here we wanted to display all the instrumentation that we have on the unit. On the unit rack itself, we've got 2 accelerometer channels, one measuring the vertical response and one measuring the lateral or horizontal response. On the front end of the unit, we have 4 accelerometers, all in the vertical direction. We have one located on the lower swing arm and a second one located above the front shock absorber on both sides. In the center of the unit, we've got our 5th accelerometer mounted right above the rear monoshock, kind of the center of gravity of the rider in the unit. So we'll be collecting vertical information there. On the rear axle, we have a triaxial accelerometer measuring 3 directions of acceleration. Here we have our light tach sensor set up with reflective tape on the sprocket so that we can monitor revolutions of the rear axle. In the middle of the swing arm, we have our rosette strain gauge measuring 3 quarter bridge strain levels. Finally, on the brake pedal, mounted on the inside, is a 2nd rosette strain gauge measuring 3 quarter bridge levels of strain.
Here we have created a finite element model for the rear suspension or swing arm of the ATV in order to predict potential stresses. Here you can see how the swing arm is linked to the main body of the ATV. Using the data collected by our accelerometers, we can apply real-world loads to our structure and view the resulting stresses. This allows us to validate designs and identify problems. Our first test using the standalone CDAC was a basic obstacle test that consisted of driving over a series of logs at different speeds and measuring the levels observed by our sensors. To view and record the data being collected by our sensors, we are using the iTestSystem Time History DAC. From here we can view graphs of our data and view our current RPMs. Our next test consisted of us driving our ATV around a creek bed. These tests were done at predominantly low speeds. Go ahead. Our final test was done at a motocross track. These tests were predominantly done at high speeds.